You ever wonder if there's a secret formula for brilliant ideas? A way to systematically come up with inventions instead of just hoping for a random flash of inspiration? Well, it turns out there kinda is. It's a powerful toolkit for exactly that. And today, we're going to unlock 5 of its most clever principles. I mean, think about it. So many of the big problems in engineering feel like a trade-off, right? If you make something stronger, well, it gets heavier. If you make it faster, it gets way more complex. But what if you could have it both ways? What if you could solve the root of the problem without having to make that annoying compromise? That is exactly where a system called TRIZ comes in. And look, it's not magic. It's this powerful method that came out of an absolutely incredible data project. A Russian engineer, Genrich Altschuler, he analyzed millions, literally millions of patents and found something mind-blowing. The most creative, inventive solutions across every single field kept using the same core principles over and over again. So he distilled all those patterns into a practical toolkit for invention.
So today, we're going to walk through 5 of these inventive principles: in advanced cushioning, equipotentiality, the other way around, spheroidality, and dynamics. Let's get right into it.
First up is Principle 11, in advanced cushioning. This one is all about planning for the worst, but, in a really smart way. You probably already get this principle without even thinking about it. A backup parachute is the classic example, right? Or what about the alternate air systems that pilots have, just in case their main instruments go down? Our kind of more subtle one is the magnetic strip they used to put on old photo film that could help fix a bad exposure. They all have one really key thing in common. The principle is actually pretty simple. If you know something has a decent chance of failing, you prepare the solution before it ever happens. It's all about looking at a system's weak points and proactively building in a safety net. That way, a tiny failure doesn't turn into a total disaster. Okay, next up is Principle 12, equipotentiality. Now, I know this one sounds a little academic, but the core idea is brilliant, and it's surprisingly physical. The absolute perfect example is the Panama Canal. How in the world do you get a gigantic ship over a whole continent? You could try to build a giant crane to lift it, fighting gravity every step of the way. Or you could do what they did. The ship just sails into a sealed chamber, water gets pumped in, raising the ship to the next level, and it just floats right on up. It's basically an elevator for ships that runs on water. So what the Panama Canal is doing is it's limiting the ship's change in position within a potential field. In this case, we're talking about Earth's gravity. Instead of fighting that massive force by trying to physically lift the ship, it changes the environment, the water level, to do all the heavy lifting for you. It's about working smarter with the forces of nature, not harder against them. All right, this next one is a personal favorite of mine. Principle 13, the other way around. It's pretty much exactly what it sounds like, and it is a fantastic way to break yourself out of a mental rut. I mean, why run through the world when you could just have the world run under you? That's a treadmill. Or in manufacturing, instead of moving some complex cutting tool around a really heavy part, why not just rotate the part itself? And if you've got 2 metal parts that are stuck together, instead of heating the outside one to make it expand, you could cool the inner one to make it shrink. This all comes down to the sheer power of inversion. When you're stuck on a problem, just ask yourself, what is the complete opposite of what I'm trying to do right now? The source material puts it perfectly. You simply turn the object or process upside down. So it really just boils down to a few simple prompts. Invert the action, swap what's fixed with what's moving, or, literally turn the whole thing on its head. Each one of those forces a totally new perspective that might just reveal a much, much simpler solution. Moving on to Principle 14, spheroidality, which is all about harnessing the power of the curve. The big idea here is simple. Our brains often default to straight lines and flat surfaces and boxes. This principle challenges us to think in curves. So instead of flat planes, use spherical ones. Instead of cube shapes, think domes. And instead of linear back and forth motion, use rotation. And you see this principle everywhere once you start looking for it. Arches and domes are incredibly strong because they distribute weight along a curve. A ballpoint pen uses a tiny little sphere to roll ink smoothly onto paper. Your computer mouse translates the rotary motion of the ball or sensor into the linear movement of the cursor on your screen. And the spin cycle in your washing machine, it uses centrifugal force to just fling the water out of your clothes, way more efficient than trying to wring them out by hand. Our final principle for today is number 15, dynamics. This one is all about breaking free from being rigid and instead embracing adaptability. The core idea here is so simple. If a system is rigid and stuck in one state, make it movable. If it's static,
make it dynamic. This lets a single object adapt and work perfectly across a bunch of different conditions.
And you can apply this in a few ways. You can have an object whose characteristics can change, like an adjustable steering wheel. You can divide an object into different parts that move in relation to each other, like one of those ergonomic split keyboards. Or you can make a normally rigid object flexible, like the borescopes that mechanics use to snake a camera deep inside an engine.
So there you go, 5 really powerful principles for inventive problem solving. But it's important to remember, this is just the tip of the iceberg. These are only 5 out of the 40 principles that make up the core of the whole TRIZ toolkit.
So what's the ultimate goal here? As the source material puts it, these tools help us get around our own mental blocks, what they call psychological inertia. They give us a structured way to think outside the box, and even a framework for figuring out where technology might go next.
So I'll just leave you with this one question. Think of a challenge you're facing right now. Could be anything. What would happen if you applied just one of these ideas? What problem could you solve today by simply turning it the other way around?